Calculating the molar solubility and concentration of ions. So there are two problems in this page. So the first one is calculate the molar solubility of silver sulfate. And here is the equation given to us. Silver sulfate solid in equilibrium with silver ions and sulfate ions, and the KSP is given to us. Now molar solubility means that you're actually calculating the concentrations here. So you do need the equation. Well, you need the equation all the time. So you can see what kind of ions you have in there. Okay, and so we have 2S, and for some strange reason when you get to solubilities we use S instead of X, but you're most welcome to use either. Okay, it doesn't really matter. When I look in the textbooks I see all S's, so I don't want to really confuse you, but if you see X's also, that's fine. Okay, because I know that's what we used in equilibrium. So there are 2 S ions, or 2 ions of S for silver and 1 of sulfate. Okay, because that's what we're going to set up in our KSP equation. So KSP, which is equal to 1.4 times 10 to the negative 5, is equal to, now for silver is 2S, but that's also squared because you have 2 of those, and then sulfate, which is S, okay, and that is just 1. So that is your equilibrium expression for this, and this is all equal to then 4S cubed once you open up the brackets, which means that calculating for S, it would be 1.4 times 10 to the power of negative 5 divided by 4, and then you would take the cube root of that, and that would be your S value, okay, which turns out to be 1.5 times 10 to the negative 2 molar. If you find anything wrong in the calculation, just let me know. Otherwise, hopefully everything is correct. All right, so this is for the S value. Now for S value, this is the concentration of 1S, okay, which means that's the sulfate ion. The silver ions would be twice of that because it's 2S. All right, so we will go ahead and use S for this because, and you'll see that over here. So we're calculating the molar solubility of silver sulfate. Okay, so if you're calculating for silver sulfate, 1.5 times 10 to the negative 2 molar sulfate ions, and you have 1 mole of silver sulfate, okay, in 1 mole of sulfate, and that's why you're using the S for this, and you don't have to do the 2S for this at all, and so which means that the value is still the same, okay, 10 to the negative 2 molar. That is the molar solubility, which means that this is the minimum amount that will be soluble, okay, in of silver sulfate in a solution. Okay, so that's how you would do that problem. Our second problem here is for concentration of ions. And since these kind of compounds dissolve very less, it's important to know what their concentration is, and some of them are actually very toxic also. For example, this problem right here. Calculate the concentration in ppm, and it could be anything, in a saturated solution of lead iodide. Lead iodide or lead ions in general are very toxic, so their concentration is measured in ppm or even ppbs. So KSP is given to us, and then the density is also given, which is 1 gram per mils. And usually if it's a dilute solution, you can presume the density is the density of water. Okay, so set up your equation, solid, and then lead 2 plus, and then 2I minus. What we are trying to find out, of course, is first the molar solubility, okay, which is kind of like the problem we did before. So once you find the molar solubility, then you have to convert that molar solubility into ppm. So the first thing is the molar solubility. So depending on what the question is asking for, you can stop in any place. All right, so then I'm going to approach this question just a little bit different, so you can see how they are solved differently. In the top one, I took 2S and S. Here I'm going to go ahead and take half S and S, okay, just so that we have a different way of looking at things also. All right, so this is half S and this is S, which is still the same ratio, because if 2 ions of sulfide are S, then lead should be half of that. Okay, so it's really the same thing. It's just a matter of writing it differently. So you can do whatever you want. You can do it as the one done on the top also. So here's the KSP, and this is going to be equal to then half S, and that's the concentration of the lead ions, and then of course the S, so you still have to square it, okay, because it may be 2, it may be representing 2, but you still have to square this, okay. So this is what we have, and this is equal to then half S cubed, okay. So then you calculate for S, so S will turn out to be then 2.4 times 10 to the negative 3 molar. Now if you were being asked for the molar solubility, then you can stop right here, but remember this is the molar solubility of iodide. If you were calculating for lead, it would be half of that. If you're calculating for lead iodide, it would be half of this also, okay, because lead iodide is 1 molar, whereas iodide ions are 2 molar, so it would be half of that, okay. But our question doesn't let us stop here, okay. In fact, for molar solubility, this is it, okay. This is your answer, final answer for molar solubility. But for ppm, you have to go a little bit further. So I'm just going to go ahead and finish this problem with the ppm concentration. I know we didn't do it this semester because it's not in your textbook, but maybe it's in another textbook, so you never know. And so we are looking for the concentration of a saturated solution, and this is for lead iodide. So we're looking for iodide solution, and so we have 127 grams of iodide in 1 mole of iodide. Before I go too far, I think somewhere here it's missing. Calculate the concentration, I should add here, of iodide, okay, in ppm in a saturated solution. So that way there is no confusion, okay, because I think it was not very clear in the question. Okay, so now it is, because otherwise you would not know whether to have grams of iodide here or lead iodide or lead, okay, and so it has to be specified in the question what concentration you're calculating for. All right, and then this is in 1 liter you have 1000 milliliters. So here, let me cross out these things so you can see where we're going with this. And this is liters and liters, and then bring your units to 1, which means grams over grams, so which means our density is going to play a role here. Now 1 milliliter over 1 gram, so milliliter and milliliter gone. So now we have grams and grams, and this is important because when you calculate for ppms, it's a ratio thing. So in the ratio you should have the same kind of units. All right, so then times 10 to the power of 6 and 10 to the power of 6 to convert it into ppm, because that's parts per million. And so then this is equal to 3.1 times 10 to the power of 2 parts per million. That is your final answer. For our purpose for this semester, you'll be calculating molar solubility, and that's generally where you would stop for most part.